Thank you. Thank you, Rajat, and organizers for accommodating these changes in the schedule. So this is the first talk of this week, and looking at the other titles of the other talks, I felt speaking something along these lines would be more appropriate, and hence this talk. So to begin with, I will give a broad overview, or what I think is a broad overview of my own research. So how I have come to think about my research. Imagine you go to a lake and there is a signboard that says average depth is about 4 feet. So for most of us, this is not a major problem. We would jump into the pool, have a swim, whatever. But suppose instead the signboard says average, it is 20 feet at places. Now, although average depth is still 4 feet, if you don't know swimming, you wouldn't get into this water, right? So with this example, I'm trying to convey two key messages. Data about extremes gives additional information than data about averages. Secondly, if you can handle the worst case scenario, then you can handle anything else. Now, how is this related to monsoon? Most of what we know about monsoon is based on modern observations. Modern observations, the very good observations for the last 30, 40 years, that is like this 4 feet of water. So whatever we know about monsoon, be it the land-sea temperature contrast or seasonal migration of ITCZ, all of this has come from observations or some interpretations of observations, but it is only 4 feet of water. The deeper water is where we test these theories and improve these theories. So what are these deeper waters? For me, for most of my work, it is paleoclimates. What happens in paleoclimates? There are changes in Earth's orbit. Ice sheets are very different. Greenhouse gases change naturally. So these offer opportunity to test these theories and improve these theories. Now, this is what most of my work has focused on until now. But right at the bottom of this trench are some very interesting idealized experiments. And that is what I have been working on in the recent years. And one such interesting experiment is the retrograde Earth. So you take Earth, spin it in the opposite direction and see what happens to monsoons. So why specifically retrograde? I will come to that in a moment. So this is from the climate model, control climatological precipitation during June, July, August. So this is a typical precipitation map that you would see during June, July, August. This is as good or as bad as any other CMIP model around. So nothing dramatic here. Now, when you spin the Earth in the opposite direction, then there are some very interesting changes that happen. The most interesting change is over Sahara. You get the ITCZ, the West African monsoon, shifting further, the entire African monsoon shifting further north. Sahara is now covered in monsoon. There are other interesting changes that occur. For example, the Atlantic ITCZ shifts south, Pacific ITCZ shifts north. Now, these changes are easy to explain. And let me tell you how. So this comes from one other very interesting characteristic of the reverse rotating world. So what happens in the reverse rotating world is that AMOC eventually collapses completely, and Pacific MOC picks up and it takes the place of AMOC. So it does the AMOC's job. So you have a southward shift of ITCZ in the Atlantic sector, northward shift of ITCZ in the Pacific sector. Quite easy to explain. But how do you explain the shifts in ITCZ that occur over Africa? So if AMOC has collapsed, then ITCZ should shift everywhere southward, but it's going north here. How do you explain this? So what we will do today, the objective of today's short presentation is to understand why these latitudinal shifts in ITCZ occur over Sahara in the reverse rotating world using the conventional theories that are around in the literature. So these simulations have been carried out with MPISM 1.2, fully coupled Earth system model. There are two experiments, control and retro. The only difference is in the sign of the Coriolis parameter. That's all. All boundary conditions are same. So first theory, land sea temperature contrast theory. I won't spend too much time on this, but a very brief overview. The top panel is climatological precipitation, June, July, August, for control and retro, what we saw earlier, but a zoomed in version. We are focusing now on the African region. The panel below is surface temperature, also during June, July, August, climatology. What you see in control is very strong high temperature over Sahara land and a strong gradient in temperature between land and surrounding ocean. But if you look at precipitation in the control simulation, there is almost no precipitation over Sahara. right? So land sea temperature contrast theory posits that a strong land sea temperature contrast should give monsoon, but that is not what you see here. On the other hand, in retro, where you have little to no, in fact, a sort of reversal in land sea temperature contrast, you have monsoon. Now, you might say that this is a chicken and egg problem. Rainfall cools surface temperature and then you have reversal, things like that. Now, I have done further analysis and I have proof that even if I take April, May, pre-monsoon surface temperatures and compare that with JJA precipitation, it still does not follow the propositions from land sea temperature contrast. If there is interest about that, we can discuss it later, but I'm just going to show this one and move on. Now, going from land sea temperature contrast to the next theory, shifts in ITCZ. In fact, the most popular version of shifts in ITCZ also depends on temperature gradients. So we take the inter-hemispheric temperature gradient this time instead of the land sea temperature contrast. And that is the more conventionally appealed to version of this theory. So what does this tell about the shift in ITCZ? So here is a plot of latitude of ITCZ on y-axis. X-axis is the north-south temperature gradient, inter-hemispheric temperature gradient. Now I have done this for two different scenarios, zonal and only in the African sector. Now in the zonal case, what happens is control is black, retro is red. So there is an increase in north-south temperature gradient and the ITCZ latitude shifts north, following the whatever predictions of this theory is. But in the African sector, when we go from control to retro, there is a decrease in north-south temperature gradient, in inter-hemispheric temperature gradient. But despite that decrease, ITCZ is shifting north. So this connection between inter-hemispheric temperature contrast and latitude of ITCZ works in the zonal mean, but not for regional shifts in ITCZ. That is the main message here. So how do we explain these shifts, regional shifts in ITCZ? So we have to go back to the primitive version of this temperature gradient. So where did this temperature gradients come from? It comes from inter-hemispheric energy gradients and the energy flux equator. So we should be looking at that and not the temperature gradients, as is quite often done in literature. So that is wrong. What we should be looking at is mainly is energy flux equator. So here is a plot, June, July, August, climatology, FNet. What is FNet? That is the net energy flux into the atmosphere from top and bottom. So in control, mainly let us focus on Sahara. It is negative or close to zero. And over the African monsoon region, the West African monsoon region, it is positive. Even in the South Asian monsoon region, FNet is positive. In the thick black contour over here is the energy flux equator. So latitude of ITCZ is closely co-located with energy flux equator, and that is what you see over here. In retro, FNet becomes positive over entire Sahara. Energy flux equator also shifts north. So energy flux equator is a much better metric for capturing zonal variations, regional variations in latitude of ITCZ. That is the message from this slide. Now, why does FNet increase in this region? So let us take a closer look at FNet over this region. So I'm going to divide it into three components: the short wave at the top of atmosphere, OLR, and surface energy fluxes. Because we are talking about Sahara land, surface energy fluxes would be negligible, but still I'm keeping it here. So here is the delta, retro, reverse rotating world, monsoonal Sahara minus the control Sahara. So this is delta applied to all of them, right? So these are the figures. So between reverse rotating world and the normal desert Sahara, FNet is of the order of 84.5 watts per meter square. And most of it is coming from changes in OLR. So why did OLR change? I have further divided it into cloudy and clear sky parts. Both are significant, but the slightly dominating part is the clear sky. So let us examine a little bit more why clear sky is changing here. And this is where we stumbled upon something quite interesting. So plotted on y-axis is clear sky OLR. X-axis here is water vapor. Why? Because clear sky OLR depends on two parameters, water vapor and surface temperature. So we have water vapor here, column integrated water vapor, and this is surface temperature on the plot on the right hand side. So plotted here is the annual pentad climatology. So every scatter here is a pentad for control. This is only for control. What we see here is that it's a very strong linear function of surface temperature. But when we take the retrograde simulation, this is where clear sky OLR becomes a linear function of water vapor. So between these two simulations, how clear sky water vapor, clear sky OLR varies, or which parameter it depends on, has changed. And that is what determines FNet and subsequently the latitude of ITCZ. So I will conclude by saying that land sea temperature contrast theory is not adequate at explaining these changes in Sahara. In fact, even interhemispheric temperature contrast is good only in the zonal mean, but for regional shifts in ITCZ, this is not the most appropriate. Like I said, most of my work is in paleoclimate. In the paleo literature, it is quite common to use interhemispheric temperature contrast to explain changes in South Asian monsoon, to explain changes in Green Sahara, for example. Now, this is a proof that it is perhaps not the most correct thing to do. We should instead look for energy flux equator, which is a much better metric for regional shifts in ITCZ. And water vapor radiative effects have something to do with how FNet has changed in these regions. So this talk is also meant to be sort of a trailer for the longer talk which I will give later this week, where we will look at how monsoons and deserts are related or how they are different. And also something that is related to this talk and also the next talk is a recent publication which which studies how monsoons and deserts are connected. So with this, I will stop and take any questions if there are.
Yeah, thanks, Chetan. Yeah, you were 40 minutes before time, which is kind of nice. Do we have any questions from the audience?
Thanks for that. That was really nice. Just talking about the monsoon and the desert relationship, I guess one of the reasons the Sahara is thought to be dry is this remote effect from the Asian or the Indian monsoon in particular. And in your simulations, that disappears. Do you think that plays a role here?
That does play a role, and we will see more of that later. But for the time being, I will quickly go into this thing. That is also important. So there are two things that are happening. That's the Rodwell-Hoskins mechanism, right? So you have diabatic heating in the South Asian region, which triggers a subsidence over Eastern Sahara mainly, which is one of the reasons why we have a desert to the west of monsoons. Now maybe I should go to this figure. Yeah. So in retro, you have now monsoons here, and because it's rotating in the opposite direction, deserts will be on the east side, right? So you have quite arid climates developing in East Asia. So that has a role to play. Now, given that is one of the factors, what we have really focused on is what is the sequence of events which leads to development of monsoon over here. So first thing is the absence of that suppression because of subsidence. Secondly, what triggers that convection? So this transition is what is where we have our contribution.
Hello. So can you please go to the slide where you showed the total column water vapor with OLR? Yeah. So I mean, for the control thing, you can see that the more column water vapor increases, you're getting a
very sharp increase.
Yeah, and but if you look into the tropic, and is it only over Africa or is it?
This is only over Africa.
Okay, so you
over arid region.
I mean, technically you would expect something like self-organized criticality, like thing that if you have more water, you should get more rain, which means you should get less OLR. So what I'm asking is that, do you have any plausible explanation that why things kind of get really flips when the moment you change?
Now, what you're thinking about is total OLR. This is only clear sky OLR. And that is where the difference is.
Okay. Okay, it's clear sky OLR. But I mean, do you have any plausible way that explanation that why the moment you flip the rotation,
so when we flip the rotation, because of the land-ocean configuration and large-scale dynamics, there is enough moisture getting pumped into Sahara. And so we have to go back to one of the earlier theories about deserts coming from Charney, high surface albedo is what causes radiative cooling, and that is what should hold a desert. But here is a proof that despite having high surface albedo, if you push enough water, you are changing local OLR and therefore F net in that region. And thus, the whole radiative cooling transfer, F net goes from negative to positive, right? So the moment that happens, subsequently, convection will get triggered. And then you have clouds and things will follow. But before clouds come, before you have convection and clouds, water vapor is present, and water vapor will already change F net over there. I will discuss more of this in the subsequent talk, but that's a valid question. And yeah, what I'm showing here is only clear sky OLR.
Yeah, thank you.
So you mentioned that the interhemispheric temperature contrast and demonstrated that it's not a good regional metric, let's say. But typically people use like interhemispheric like energy contrast, right?
Yeah, they do. Now, I think that is also one of the reasons why I sort of mentioned my background in paleoclimate. People still use land sea temperature contrast, and they also use interhemispheric temperature contrast quite extensively in the literature, when in reality they should be using energy contrast or energy flux equator. So these are some very drastic changes that I use in climate or in monsoons to push forth or dispel such wrong ideas that are in the community. But you're right, we should be, that is how the theory originally came, right? In interhemispheric energy contrast, and a proxy of interhemispheric energy contrast is temperature, which works mainly in the zonal mean. But does it hold for regional shifts? Yeah, here is one proof that it does not. And my objective here is to convey it to, or make a solid case of that.
Yeah, thanks, Chetan. Yeah, let's just thanks, Chetan, one more time.
Thank you.
Yeah, so this is some work I've done with a postdoc Dongxi in at Monash, and I'm thinking about the difference between sort of local intense precipitation on a small scale and widespread intense precipitation, and how their environments might differ. So this is probably a bit redundant for this audience, but different scales of precipitation extremes or heavy precipitation will have different impacts. So you might imagine kind of downpour at a very small scale that might overwhelm the drainage system of your local city block, and that'll have certain impacts. Or you might imagine a much more widespread precipitation event that floods a river and creates, widespread flooding over some agricultural region. So they're very different, and they can have different magnitudes, but we care about them both. And these types of events also have different environments. So this is from a paper by Louf et al., who was at Monash at the time, and he used rainfall estimates from a radar in Darwin. So this is a picture of the radar. So you get these snapshots, and so you have different cells of rainfall in this region, which is about 200 kilometers across, and Darwin, I think, is sitting here, and this is the Tiwi Islands. And they looked at different types of events. So they divided the precipitation into different features. So essentially these blobs of color on the diagram. And they said, what happens when you get high intensity events locally? What happens when you get a large area coverage? And maybe unsurprisingly, the morphology is a bit different. So if you have high local intensity, it tends to be few but large rainfall objects. So you get these kind of big blobs, and this one here creates quite high intensity. Whereas if you're talking about the widespread deluge, so a large area mean rainfall, mean over the whole radar, that tends to be a large area coverage. So there's a very strong relationship between the area covered by convection and the average rain over the domain. But they also happen under different environmental conditions. So they showed that you tend to get a slightly drier atmosphere with more CAPE for local downpours and a moist atmosphere for widespread deluges. And so I just want to ask why and try to build a model that helps explain this. And so this is basically a problem in trying to understand the relationship between the convective state of the atmosphere and the large scale state. And maybe that sounds familiar to you because we've been working on this for like 50 years. And so I thought I'd start with the most famous one of all, the Arakawa and Schubert models. I'm going to use that, essentially that convection parameterization to try and get insight into this problem. And so this model assumes that the convective ensemble is a spectrum of plumes with different entrainment rates. And each plume entrains mass as it rises, so its mass increases as it rises, and then it detrains at its level of neutral buoyancy. So I've written some equations up here, but they're not so important unless you're a plume aficionado. The thing to concentrate on is this figure. So it shows moist static energy on the x-axis and pressure as a height variable on the y-axis. And you've got the environmental variables, the red and the blue. So the environmental moist static energy and the environmental saturation moist static energy in blue. And then these dashed lines are individual convective plumes with different entrainment rates. So the vertical one is 0 entrainment rate. So moist static energy is roughly conserved for a plume that doesn't entrain. So that's going vertically. And then as you increase the entrainment rate, these dashed curves get pulled towards the red curve because of the dry environment. And so they rise up, and then they detrain where they reach their level of neutral buoyancy, which is where this blue line, where they hit this blue line, essentially. So a sort of more recent paper by Zhao and Jie showed that you can actually calculate the thermodynamic environment of this system if you're given two things. One is the relative humidity of the troposphere, so how dry is it? How much dry air are you entraining into these plumes? And this quantity epsilon of Z, which is the entrainment rate of a plume that detrains at a given height. So basically what you're saying is if I know what the entrainment rate is of this plume that detrains at 150 hectopascals here, because I know the relative humidity, I can calculate this plume, so I know exactly what its temperature is going to be, and so I know the temperature at that height, and I know the temperature at all heights. So it's sort of not surprising you can do this, but they came up with this really nice equation for it. And again, you don't have to worry too much about the details of the equation, but the point is that all of these thermodynamic quantities have bars above them. So they're all mean state quantities. They're not plume quantities. So even though we're thinking about a plume model and we're trying to solve for the plume moist static energy, you can cast this in an equation for the environment. And this is sort of along the same lines as what I did back in 2013 for the zero buoyancy plume models. This is the same idea, just applied to a plume spectrum. Okay, so to kind of make progress, what we need to do is we need to know the relative humidity of the troposphere, and that's I'm going to take as a parameter that I can vary. And we need some way of calculating this epsilon Z. What is the entrainment rate of a plume that detrains at a given height? And so I'm going to do the simplest thing I could think of, which is to think of to start with the cloud base and think about the cloud-based mass flux and constrain epsilon Z with the cloud-based mass flux. And so the idea is that I assume that the cloud-based mass flux is made up of these boundary layer thermals, which have a variety of entrainment rates depending on their sizes, etc., that are positively buoyant. And again, for complete simplicity, I just say, let's assume there's a uniform distribution of entrainments. You have this spectrum of eddies in the boundary layer, and they have different entrainment rates, and it just so happens that their population is roughly equal at each entrainment rate. And so this gives you a picture like this. You have entrainment rate on the x-axis and max flux distribution on the y-axis, and so it's a straight line. And then at some point, there's a cutoff. And below that cutoff, the plumes are no longer buoyant. And so your mass flux is then the total area in this region. And so if you want a higher mass flux, there's only one way to do it in this model, and that is to increase the entrainment rate for which a parcel is positively buoyant. You need a less stable lower troposphere, basically. And that's really the key of this model, because that tells you how you get a large area mean precipitation rate, because the mass flux at cloud base is essentially related to that precipitation. This model basically says to get a strong area average precipitation rate, you want as many plumes as you can to be buoyant. So the environment must be such that that is the case. Okay, so that's at the cloud base, and then we assume some sort of mass flux profile vertically, and we assume that is constant. And so each plume grows exponentially, but that means epsilon Z must decrease to compensate, because you don't want the overall mass flux stays constant. So that actually allows you to calculate this epsilon Z profile. The precise mass flux profile doesn't matter so much. You can have sort of variations, but constant one is the simplest. Okay, so that gives us a model that we require, the spectral plume model. If you're given the area mean precipitation rate, which tells you the mass flux you need at cloud base, and the relative humidity, you can calculate the environmental temperature and humidity profile, and you can calculate properties of different plumes. So you can go back to this picture and you can say, okay, once I have this environment, I can lift these plumes through that environment and ask, what is their buoyancy? And using simple parameterization, what's the updraft strength? So we kind of have all the things that we need. So I'm going to show you some results from this, and I'm going to show you them in something called the stability humidity plane. So this is something I developed with a student, Lucinda Palmer, where we plot properties of the atmosphere as a function of the vertical change in the saturation moist static energy, so a measure of stability, more unstable is down, and the saturation deficit. So towards the left is towards a more closer to saturation atmosphere. The reason to do this is that different slopes in this plane correspond to neutrality to different training plumes. So if the entrainment rate is 0, then the vertical change in H star is going to be 0, because H star is conserved for that plume. But for a non-zero entrainment rate, as you get drier in the atmosphere, the decrease in moist static energy from the plume is larger. Okay, so I solved this spectral plume model for various area mean precipitation rates and relative humidities, and then I'm going to plot it on this diagram. So the axes are basically environmental conditions, and I'm going to plot convective conditions on top. And so this is the area mean rainfall, and you can see, as expected from the design of the model, it increases with the entrainment rate. You've got the high precipitation in blue along this part here, and it goes down as you go up, sort of as you go anti-clockwise around. But we can also, so that makes sense because, this graph, basically you've got to increase the entrainment rate to get more mass. That's kind of built into the model. The other thing you can ask is about the high percentile updraft. So this, I take the entrainment rate, 1/10 of the entrainment rate, the maximum entrainment rate you can get. So I'm calling that the 90th percentile updraft. And this is how it looks on this plane. So rather than peaking where the mean precipitation peaks, it peaks down in this bottom right corner. And that's where the atmosphere has large cape because the atmosphere is very unstable, and it's also dry. And why is dryness important? It's because essentially when the atmosphere is dry, only the least entraining plumes will be able to penetrate into the atmosphere. So it's sort of this what do you call it? Evolution kind of idea where you kill off the plumes that are high entrainment, so the ones that are left are very low entrainment, and so you get a stronger updraft. So you tend to peak in this bottom right corner. So this kind of validates what we started with, that we get different places in this environmental phase space where we get high area mean rainfall and high local rainfall, which here I'm sort of taking the 90th percentile updraft as a proxy. And we can test this. We can use that same radar data to look at this same phase plane. And here are those results. So this is using the Australian Unified Radar Archive, which gives you estimates of precipitation in a radar scene. And we plotted those scenes in this same phase space. So this is the area mean rainfall. And you see roughly it does the same thing. It increases as you go to higher entrainment rate. And this is the maximum cell intensity. So we defined convective cells and just looked at the intensity of those and picked the maximum in the domain. And that tends to peak down here. So I call this a pretty good agreement with theory. I don't know if maybe you can disagree. So that's it. So I'm thinking about local downpours versus widespread deluges, and they occur in different environmental conditions. A simple model based on essentially Arakel and Schubert can predict this. And the core idea there is that to produce more rainfall in the domain, you need to allow more plumes to be buoyant. That essentially tells you what the lapse rate must be. And radar observations agree really well with this. Thank you.
Hey, Marty. Great talk. What justifies this uniform distribution of the entrainment rate, and how sensitive or not is the results to that choice?
Yeah, that's a good question. What motivates it is just simplicity, and it helps with the analytic solution. So you can't get an analytic solution otherwise, or you can't, and it's actually quite difficult because you have to integrate this, right, with an exponential, which is the growth of each plume with height, and you can only really do that for a uniform distribution or something quite simple. I haven't tested how sensitive it is to that. My gut feeling is it wouldn't be so sensitive because the basic results are actually pretty straightforward. As long as you've got to increase the entrainment rates that you allow to get more mass flux, then you're going to have that same same distribution for the area mean precipitation and the high percentile updrafts, sort of similarly simple in how the model actually works. So I don't think it's too sensitive in a qualitative sense.
Thanks, Marty, for the nice talk. My question is about the downdrafts, actually. So we are right in this model, we consider that as much mass is available for plumes to go up. I wonder if the adjacent downdrafts will actually also play some role. At least in this model, they do not, and the match is fantastic. So I was wondering what goes on.
No, that's a really good question. I actually haven't thought about that. And potentially there you could have a lot of updrafts which are balanced by a lot of downdrafts, and then your net precipitation is not so large, but you can still have a very unstable atmosphere because you're producing a ton of plumes that are buoyant. That's actually a really good point.
Yeah, cloud scale, I think people have shown that there are these subsiding shells, I think is the right, yeah. So maybe there are such overturnings.
Yeah, so I mean, I guess the sort of, you could kind of think of this as the net mass flux. Each plume has kind of a net between the subsiding shell and the mass flux within it. And then you assume that the ratio of those two don't change or something. So you could sort of construct a way to make this make sense with downdrafts, but I think you're right that it's a missing component. So it might be important, that's true.
One more question. This question is actually for more my understanding. So you have this phase plane and this linearity between y and x axis. I mean, that's so beautiful in the observations. Why does that happen that way? I was thinking saturation deficit has non-linear relationship in the exponential relationship with the instability.
Yeah, I guess the way I came to this idea was through Fayez Ahmed's work. So he showed that precipitation is a very strong function of the plume buoyancy. And this is almost turning that around and saying, what's the entrainment rate for that plume that you need to be neutral in that? So if you frame it in that way, you're likely to get the same result. And I think, I mean, he has sort of no rainfall and then a linear ramp up. So maybe the linearity sort of comes from that linear part. Yeah.
Thanks.
Yeah, I think we can all thanks Martin one more time. Yeah.